So here's the definition. So sedimentary structures are macroscopic. Remember, it's macroscopic, three-dimensional features of sedimentary rocks, recording processes occurring during the deposition or between deposition and lithification. So it sometimes gives us the entire history of rock deposition if we can study all the sedimentary structures that are found in an outcrop. And the importance are aid in interpreting depositional process, conditions, and current directions. Okay, so also some of the sedimentary structures gives us top of the bed indicator and direction of the current, indicators of direction of the current. Okay, and then classifications are primary structures. Definition: sedimentary structures are features that form during or shortly after the deposition of sediments, reflecting the physical, chemical, or biological process operating at the time of deposition. Okay, so during the time of deposition, the structures that were formed are called primary structures, where after deposition or post deposition, the structures that are formed are called secondary structures. So from post deposition, mainly through chemical processes and also to mechanical and biogenic processes, to some extent we get these secondary structures. So mainly two structures can be there, primary and secondary. Pre deposition is primary, post deposition is secondary. Very simple, right? Okay, now we will take this one by one. So primary structures will first take. So pre-depositional or erosional sedimentary structures. Okay, remember pre-depositional or erosional sedimentary structures are called primary structures. So say we have first is channel. Channel means the river channel. Okay, river channel it can be say it can be a marine or underwater channel also. Okay, so let's stick to the theory of river channel only for understanding. So, origin: large interbed structures varying in shape and size formed from erosion, following by sediment infilling within the stream or tidal channels. So, initially there will be a scouring where the river will flow. Okay, it will be at a certain depth, right? So, scouring will happen, then river will flow, and then later it will be filled by river-borne sediments or river-carried sediments. Okay, infilling within the stream or tidal channels. So found in fluvial, shallow marine, and submarine environments, they confine the flow of water, right? They confine the flow of water. Okay. Marks significance are marks sites of high energy deposition and sediment reworking, reservoirs, aquifers, and mineral ore bodies. Occurrence of mineralization can host placer deposits like gold, tin, diamonds due to the concentration of heavy minerals in ancient river channels. So placer deposits are mostly heavy mineral deposits. Okay. So native elements like gold. Okay, we can find heavy minerals like garnet. Okay, tourmaline, all those rare minerals and all those heavy minerals, and also some native elements like gold can be found as a placer deposits. Okay, or say some nodules within mixed within the sediments. Okay, so gold in diamonds due to the concentration of heavy minerals in the ancient river channels. Okay, so river channel is very simple to understand, right? So channels are present. Channels, how you will understand channel deposit. So channel deposits are mostly understood using their um, say cross section, right? Because of their cross section, only through the cross section we'll understand the channel. So the channel deposit looks like a half cylinder. Okay, so the basic geometry of a channel deposit will look like this. Okay, so this is the basic channel deposit of half cylinder, and we can only understand that this is a channel deposit in a outcrop section if you get to see this type of structure. So the identification of a channel deposit can be done using the cross section of a channel. If you are seeing a section bearing this, you won't be able to understand that this is a channel deposit. But if a section is there which contains this section is there, say if you are seeing an outcrop having a section like this, say having a section like this, okay, you are seeing this section and you are seeing layers like this, and then you are getting a channel like this, a channel deposit filled with sand. then you will say that this is a channel, sorry, channel deposits, right? Now I will come to soul marks. Okay, soul marks. Okay, soul. Remember, soul marks means bottom markers. Okay, so bottom you have soles like shoe soles, right? So it will be at the bottom, just like shoe soles. So origin erosional features on bed surface preserved by subsequent sediment burial. Example common in turbidites. Okay, common in turbidites. So these are actually erosional features, the scouring features on the bed surfaces. So found in marine turbidites and deltaic environments linked to oil shales and placer deposits. So what happened is that, say example, say we have a muddy layer like this mud, and you know mud is cohesive and it retains the or it it can be molded and it can preserve different structures. Okay, so in mud, say we have different grains, okay, which is flowing and getting struck at the top of a muddy deposit, okay, because of the flow. So it will form this type of structures like soul structures. Different soul structures are there, we'll talk about that. And for preservation of the soul structure, it needs to be hardened, because since mud is cohesive, you can form a structure in a mud, but it will not be able to preserve any structure in it itself. Okay, it needs to have a certain burial of sand over it. Okay, it needs to have a certain burial of sand over it. So sand can retain the shape of the bottom layer of the soil structure and can preserve it. Okay, so that is why soil structure is a bottom surface indicator. Okay, so this is mud and this is sand. Remember, this type of setting is needed for preservation of these structures. Okay, because mud can make those structures, or any tool or any grain can make erosional structures on a mud, but it cannot preserve those structures on its own because of its cohesive nature. So a sudden burial of sand over mud will be able to preserve or retain that structure. Sand can retain that structure, okay, but cannot form that structure. Mud can form that structure but cannot retain the structure. So these are actually erosional features, soil marks. So types are scour. So because of scour means erosion, forms as a result of turbulence in water causing erosion. So the turbulence in the water causing erosion. We have the first one is the flute marks. So soil marks can be of different types. First one is full flute marks or cast, maybe asked in 10 marks. So a little bit in detail. So sometimes these are asked in questions. So write a note about flute marks. So you'll have to write all those things. Also, have to draw this kind of diagrams. So see, this is a flute marks, and this happens because of this turbulence of water. Okay, and the current direction is towards left to right, and the convex shape will be, or the arrowed shape will be towards the up current direction. This is the up current direction towards the right, and this is the down current direction towards the left is the up current direction, and towards the right is the down current direction. Now definition: elongated spoon-shaped depression formed by turbulent flows. This in cross section it will look like this. This actually are nose shaped, and this is actually in 3D. And in plan view it will look like this. So elongated spoon-shaped depression formed by turbulent flows a type of sole or scour mark. In cross section, you will have an asymmetric in cross section with one steep edge opposite to a tapered edge. So one edge is steep, another edge is gentle. In plan view, they are narrower at one end and widening out onto the tapered edge. So formation is preserved as casts of features formed by infilling depressions. Significance: asymmetry of flute marks indicates that they can be used as paleo current indicators. So very important, they are used as a paleo current indicator and also used as a bottom of a bed. So marker for bottom of bed. So bottom of bed indicator. Okay, created by turbulent eddies. Then we have obstacles cover. Say there is an obstacle and say water is going from left to right. So due to this obstacle, the bed will deform like this. So it will produce it in the plan view. It will look like this. In the cross section, it will look like this. So obstacles cover definition is an obstacles such as pebble can eddies that scour into the bed. It will be can form eddies that scour into the bed. There's a form here from right form. Now an obstacle such as pebble can form eddies that scour into the bed. So these marks are asymmetric and can be used as paleo current indicators. Okay, remember they are used as paleo current indicators. The horns represent the current direction. Okay? The horns represent the current direction, or the gentle slope represent the current direction. The obstacle causing a scour must be stationary, right? So obstacle has to be have very high density so that it becomes stationary and does not move with the flowing current. Then we have ridge, furrows, and gutter casts. So linear features on the bed surface caused by turbulence. If narrow, they are called ridges and furrows. If wider and deeper, they are called gutter casts. Okay, so a gutter cast will look like this. So these are similar to ridges, but wider. Say we have um, in plan section, it will look like this. In plan view, it will look like this. So it will look like this. There will be grooves because of some scouring by different grains. These are called ridges or grooves. Okay, so it will look like this. In the top of the surface. Again, bottom of sand and top of mud. Okay, these are ridges or grooves or gutter casts, whatever you call it. Ridges, furrows, gutter casts, all the same thing. Okay, so in cross section, it will look like this. Now, straight to slightly curved linear depressions, grooves are chevrons are when marks not straight, usually indicating a change direction of the object. So when the mark is not straight, we call it chevron, usually indicating a change in direction of the object. So if there's a change in direction, then there will won't be any straight grooves, but slightly bent. Then we call it chevrons. Then we have prod, skip, or bounce marks. As the name suggests, prod marks. So these are actually bounce marks. Pod marks, steep and gentle slope will be there where a rock has bounced. Okay, these are bounce marks. Pod marks are nothing but skip marks, like say a rock is intermittently jumping on the ocean bottom, or sorry, on the channel bottom because of the inflowing of the current. So it will form these depressions on the bottom, right? and it will form like this in cross section because of stacking of different grains and then going up again. Okay, so these are the grains, and this is the bottom of the bed. So grooves are straight to slightly curved linear depressions. Chevrons are the tool marks. So we're talking about tool marks. So impression left by objects being dragged or bounced along the bed in the water is called a tool mark, and these are the sub classification of a tool mark. First is grooves, straight to slightly curved linear depressions. Chevrons, when there's a slightly change of direction, we got chevrons. Grooves in cross section will look like this. Then we have prod marks, skip marks, or bounce marks formation created by objects saltating or intermittently bouncing along with the flow. Then we have prod marks, objects dug into the muddy sediment and then lifted out, leaving an asymmetric mark like this. Okay, steep slope, and this is gentle slope. Then we have skip marks, linear tool marks from objects that skip along the bed with a steep and gentle slope. Okay. Then bounce marks, series of marks from an object repeatedly bouncing on the bed. There will be a series of marks. Okay. So here is one mark, here is another mark, here is another mark like this. So linear marks from object rolling along the bed, we got roll marks. So different types of motions of the bottom sediments being saltating, rolling, sliding will give you different kinds of marks. Okay. So these are some of the structures or tool marks. Then we have the syn depositional structures. Okay, syn depositional structure. And the previous one was the just the primary structure, pre-depositional or erosional sedimentary structures, and now we'll talk about syn depositional structures, so which have formed during the deposition of the sediments. So we have the bedding and laminations. So refers to the layering or stratification visible in sedimentary rock, where distinct and unique in lithology and texture, etc. Layers of sediment accumulate one above the other over time. So greater than 1 centimeter, we'll call it a bed. Okay, so if the layer have a distinct boundary and which is greater than 1 centimeter, we'll call it a layer. If it is not, then we'll call it a lamination. So less than 1 centimeter, we call it a lamination. There is finer layer, mostly less than 1 centimeter thick, found in very coarse grained rock such as shale. So bed forms are parallel here, and then here it is not parallel. It can be non-parallel also. Dipping beds. It can be wavy like this, or it can be curved like this, maybe because of storm. Okay. So different kinds of beddings can be there. Different types of orientations can be there. Significance indicates continuous sedimentation. Occurrence of mineralization. Mineralization occurs within the layer, especially in environments conducive to percolation. Example, limestones and shales. So mineralization can be there. Now we'll talk about the planar beddings. So planar beds are sedimentary structures characterized by the distinctive flat or planar orientation within the sedimentary layers. You can see this is the planar beddings. Typically lack significant internal bedding structures like cross bedding or ripple marks. So planar beddings are nothing but simple planar beds that is parallel to one another, have sharp boundaries, and does not form any kind of cross stratification or cross lamina. So formed in quiet water or low energy depositional settings such as lake bottom, deep marine. Okay, significance are indicates periods of calm deposition and stable sedimentary conditions. Okay, where there is no preservation of ripples, where there is no preservation of any cross stratifications, then there will be planar beds, which often occurs because of quiet water or low energy condition. So there won't be any kind of ripples. So there won't be any kind of preservation of the lee side, and then no preservation of cross stratification. So we have type laminated bed, graded bed, and massive bed. So lamination means planar beds containing internal parallel laminas. Graded bedding means that means the layers are graded. Graded means it can be from coarse grain at bottom to fine grain at top, or it can that is called normal grading. That is coarse grain at bottom, then medium grain, then finer grain at top. That is called normal grading. In reverse grading, we have fine grain at the bottom and intermediate grain, then coarse grain at the top, which is called reverse grading. Then we have a massive beds which do not have any kind of beddings or internal structures, just a big massive bed which is of centimeters to maybe meters thick, without any internal boundaries in between. So we first talk about graded beddings. So formed by the deposition of coarser materials first, followed by finer materials as the current slows down. So as the energy of the currents are high, we will get deposits of coarser sediments. If the energy of the current is low, we will get deposition of suspended sediments or finer sediments. So layers showing a gradual change in grain size from coarse at the bottom to fine at the top. Significance indicates decreasing energy condition during deposition, typical of turbidite and subaqueous gravity flows. So in turbidites, you used to get this finding upward sequence. Then occurrence of mineralization, common in deep marine environments and associated with placer minerals, deposits like gold, copper, and tin. So in deep marine environment, we get this placer deposits. Placer deposits can also be found in river channels, in beaches, in deep marine also, and also associated with heavy minerals. We'll talk about placer deposit again in economic geology. Okay. So cross bedding origin, inclined layers formed by the movement of wind or water currents. Significance indicates paleo current direction. We know this. This is a cross beddings. Okay. The slope of the cross beds will define the paleo current direction. So common in fluvial, aeolian, and shallow marine environments. Occurrence of mineralization can indicate paleocurrent direction, and mineralization often occurs in ancient river system, beaches, or deserts with heavy minerals like iron ore. Then we have ripples. These are symmetric ripples, and these are asymmetric ripples. Here you can see both the sides are of same, both the dips are of same amount and same direction, different direction, opposite directions. Whereas this one has a gentle slope and a steeper slope. Okay, alternatively. So the steeper slope indicates the current direction. The small, scaly, wavy undulations on the bed surface created by water or wind action. Significance reveal flow direction and water depth common in riverbeds, beaches, and tidal flats. Occurrence of mineralization, asymmetric ripple mark environments like river or tidal flats which may contain mineral deposits like copper or coal. Ripple marks can be asymmetrical or symmetrical. Okay. Then we have reactivation surface. So surfaces indicating a shift in depositional conditions such as changes in current direction and velocity. So when there is say a backward current, there will be a scouring. Okay, so a backward current can be there, which sometimes scours the top surface, and there that will be called a reactivation surface. Surfaces indicating a shift in depositions or condition such as changes in current direction or velocity. Then we have gravity flow deposits. So debris flow deposits, poorly sorted sediments from gravity-driven flows. Graded deposits formed by turbidity currents such as Bauma sequence. Okay, now we'll talk about the cross bedding in details. So again, we have given this diagram so that it helps you. This is a typical cross bedding. Okay, so this was the initial cross bedding, but later it will be scoured. So it is a sedimentary structure formed by inclined layering of sediments within a larger sedimentary unit. So cross bedding forms as so these are the cross beddings, okay? So, and this can be a dune or it can be a ripple, right? And these are the cross beddings. So cross bedding forms as sediments deposited by wind or water currents on inclined surface. As the sediment accumulates, it creates inclined layer that are typical at the angle of the horizontal. So the preservation of this lee side of ripples as the ripple migrate with the flowing, it can be air, it can be water also. In the channel also it can be there. In marine setting it can be there. It can be there in and can be aeolian condition also. So the migrating ripple or the dune will result in preservation of the lee side, and these are the preservation of the lee side that we call the cross bedding. Okay. So I've defined this, I think maybe one or two times. in previous lectures also. So if you're not, if you have forgotten, then please check that once again. Okay. So it creates inclined layers that are typical at the angle of the horizontal. So it commonly occurs in environments with flowing water, that is deltaic environment, tides, shallow marine, or wind, deserts, and beaches. Anatomy: we have a four set. This is the four set lamina, main inclined part of crossbed. Then the top set, the low angle upper truncated portion. This is the top set part, low angle upper truncated portion. Truncated means cutted, right? Cut portion. Then bottom set, we have a lower section almost parallel to the basal bedding plane. This is the lower section, bottom set. So geological significance. Similarly, write geological significance of any other question with modification to suit the answer. So paleo-environmental reconstruction, so indicates paleo current direction and velocities, water or wind, helps reconstruct past environments like rivers, deserts or beaches, and sedimentary process indicators. So since this is the foreset, we'll get the idea from the foreset lamina. So the direction in which the foreset lamina dips will give you the paleo current direction. Shows how sediment was transported and deposited by current or wind. Highlights processes like ripple migration or dune formation. Okay. So in this is a small topic for you guys. Like the syllabus is not so vast for ripples and dunes, but ripples and dunes are like very important subject, very important topic for sedimentologists, because there can be lot of different kinds of ripples. Sometimes there can be ripples where the not only the lee side but also the stoss side get preserved. Okay. Then things change there. So we'll not go into that detail, but for your syllabus, I think the preservation of lee side will be enough. Okay. So there are a lot of things, but yeah, a major importance of a ripple of a cross stratification or a cross lamina is the paleo current analysis. Okay. So deposition energy estimation, crossbeds, angles, thickness, and sorting, etc., reflect the energy levels of the past environment. So the amount of dip of the different laminas will give you the energy condition of the environments. It provides insights into sedimentary dynamics and depositional conditions. Then we have stratigraphic interpretation. So assist in correlating sedimentary layers across different areas, used in stratigraphy to understand sediment sequences and environmental changes. Okay, all these things can be done. Then types, form, or expression of cross lamina, cross bedding, or lamina. So tabular or planar cross bedding has distinct flat top layer with sharp boundaries. So if the say if the bounding surfaces of the cross beddings are flat, okay, then we call it a tabular cross bedding. If one or both surfaces are curved, here you can see this is a curved layer. Okay, this is not actually festoon bedding, lenticular bedding, mud pleasure. Okay, just think about it. Say forming a V shape formed due to reversal in current direction. Alternating sets of crossbeds with opposite dipping directions. So okay, let's look at this one. See if this is the one. Uh, so okay, we were talking about this, right? One or both surfaces are curved, formed by downward migration of curved bed form. Okay, so maybe this one is curved, right? So this was is actually a trough cross bedding. If we have lamination like this here, we'll call it a trough cross bedding. Then we have herringbone cross bedding. So alternating sets of cross beds with opposite dipping directions forming a V shaped form due to reversal in current direction. So if possible, I'll show you. Okay, so herringbone cross stratifications are characteristics of tidal environment where there is bidirectional currents. herringbone cross stratification will look like this. They will be oppositely dipping laminas. Okay, this is a herringbone cross stratification. Okay, so it can be because of this tidal current and ebb current. Okay, both oscillatory currents in tidal environment will get this type of herringbone cross stratification. Then we have fissure bedding. In fissure bedding is where cross laminated sand contains mud streaks, usually in the ripple troughs. So you have mud streaks in a rippled troughs of sand. Okay, we get fissure bedding. In lenticular bedding, sand lenses within the mud. So mostly it will be mud, it will be sand lens, small sand lens. So this is just the opposite. Lenticular bedding is just the opposite of a fissure bedding. So here you will have majority of sands covered by some amount of mud located in the troughs of ripples. Whereas in lenticular beds, you'll have majority of mud and small patches of or lenses of sands in between. Okay, so sand lenses within the mud formed in low velocity water such as standing tide, mud accumulates on sand bed. Then we have wavy bedding, so alternate layers of sand and mud. So when there is equal amount of sand and mud deposition alternating natively, we will call it wavy bedding. Wavy bedding falls in between lenticular bedding and fissure bedding. Okay, because in both this one type of grain size dominates the other, but in wavy bedding we have more or less equal amount of sand and mud. Then we have festoon bedding. It will look like this is a festoon bedding. So mounted dunes and ripples cutting into each other look like this. Then we have hummocks. So irregular and hummocky, concave up or down in shape formed by in turbulent water. These are hummock beddings. Very rare to find, but yeah. So ripples. Now we'll talk about the ripples in detail. So can be asked 10 marks. So below is the detail. So we have symmetric ripples, again asymmetric ripples, wave-like bed forms in fine sands under gentle traction currents. Okay. So migrating ripples deposit cross laminated sediment, typically 2 to 3 centimeter thick, contrasting with cross bedding that is greater than 50 centimeter thick. Okay. So ripples are very smaller size than dunes and then cross beddings. Okay. So symmetric ripples, we have this symmetrical ripples produced in shallow water by orbital wave motion, where oscillatory waves are there, appearing markedly subparallel in plan views, and occasional bifurcation can be there. Asymmetric ripples generated by unidirectional current. Remember, there will be only one direction of current in asymmetric ripples, where in symmetric ripples you will have bidirectional current. Features in differentiated low angles, stoss side and steep angle lee side with cross lamina parallel to the lee face. So a symmetrical ripple is a top of the bed indicator, whereas a asymmetric ripple is not a top of the bed indicator but a directional indicator. Remember, symmetric ripple is a top of the bed indicator and asymmetric ripple is a direction of current indicator, a current direction indicator. Generated by unidirectional traction currents featuring a differentiated low angle. So symmetric ripples. How symmetric ripple is a top of the bed indicator is because the points direct towards the top. Remember, the points direct towards the top. That is how we get top of the bed indicator for a symmetric ripple. So varieties, we have lunate and linguoid, pointing downward and pointing outward. Okay. So significance, asymmetric ripples and paleo current indicator. So this is the type of a lunate and linguoid. I'll try to show it to you. Okay, just a minute. Yeah. So mostly in the plan view, you get to see the lunate ripple or lingoid ripple. There are other types of ripples also, but we'll not go into that detail. So remember this: if you want to show a lingoid ripple will have a D-shaped ripple. So if this is a D-shaped, this is a D, right? So this is a lingoid ripple, and a lunate ripple will be the opposite or U-shaped. Remember U-shaped. This is U because lunate contains U, and it will look like this lunate ripple. Look like this, and um, lingoid, right? D lingoid for D, lingoid ripple, and the current direction for both will be from left to right. Then only it will form like this. Okay, these are actually plan viewed structures. You won't find this type of thing in cross section. Okay, I hope you understand this. This lingoid, this lunate. Okay, so this will be it for today's class. Up to this ripples. In next class, we'll talk about post-depositional, penicontemporous, and deformational sedimentary structures. Okay, I think in maybe in two more classes we will cover up the sedimentology. Okay, thank you for listening and prepare well for your exams.